We're going to have welcome comments here from the Director of the Institute of Marine Research, Rector of Bergen. And we'll start with Mr. Nepstad, who is the Director of the Institute.
Thank you. Let's see if we can get this thing on. Okay? Good. First of all, to all of you, welcome to Bergen. I'm extremely pleased because at this time of year, you have obviously brought beautiful weather with you. That we appreciate and we say thank you for. As this conference is organized by the Integrated Marine Biochemistry and Ecosystem Research, the IMBER project, we find that this is an international project aimed to investigate the sensitivity of marine biochemical cycles and ecosystems to global change. Timescales ranging from years to decades and hopefully longer. The need to provide a comprehensive understanding of and, if possible, accurate predictive capacity for ocean responses to an accelerating global change and consequent effects on the earth systems and human society is, I think, of vital importance. This conference, Future Oceans, Research for Marine Sustainability, Multiple Stressors, Drivers, Challenges and Solutions, includes a wide range of topics related to marine biogeochemistry and ecosystem research, from ocean acidification to management of fisheries, human dimension of global marine change. I'm very pleased that this conference so far has attracted more than 700 contributions and that we gathered approximately 500 research scientists from more than 40 countries around the globe. This says something about the importance of IMBER. This was made possible due to a strong support from Bergen Marine Research Community, and I would like to thank the local organizing committee, including Ken Drinkwater and Sven Tunby both from Institute of Marine Research, Dag Aksnes, Beatrice Barino, Tore Burvik, Christopher Heinze, all from University of Bergen, and of course, Eva Madison from the IMBER International Project Office here in Bergen. For Norway and Bergen especially, the expanding contribution to the development of marine research is important, especially as we, on the 18th of February this year, formed the Youth Center for Marine Ecosystem Dynamics with the purpose to conduct cross-disciplinary research of natural and human-induced changes in the ocean. Its mission is clearly central to the IMBER research topics. The Youth Center is a collaboration between the Institute of Marine Research, University of Bergen, Uni Research, and the Olsen Environmental and Remote Sensing Center, all located in Bergen. And when the Minister opened the center in February this year, we were very pleased that we finally had managed to get the different research community and science community in Bergen to cooperate. Since climate change and other drivers alter the marine environment at unprecedented rates, our ability to predict marine ecosystem dynamics in the near and long future hinges on the thorough understanding of the mechanisms that govern species dynamics and interaction. Through a partnership between institutions having complementary strengths and competences, the Youth Center is in an ideal position to address this challenge. This initiative also fits into the focus on cross-Atlantic research. Among others, the possible projects as a result of the Galway statement made in Galway last year between the European Union, of which we in Norway scientifically is part of, United States and Canada, with a focus on bridging design across Hopefully, this initiative will also be able to work together with the world's oldest international marine research organization, the International Council for the Exploration of the Sea Ices. And from my position, I find that it's only through working together we will be able to deliver the science that the society at large actually expects from it and has a total right to demand from it. And I would also like to point out the need for cooperation across the classic science standards. From the outside, not the science world, but from the community, people do not understand the division of science, natural, and they expect it is needed cross-scientific cooperation. It will be delivered. The scientific presentation and discussions that have already started to take place during the workshops, yesterday and on Sunday, and in the following plenary and parallel sessions, the strategic discussions that will take place later this week about the development of an international marine research project beyond 2050 are of key interest in the context of the Central development and the marine community in Bergen and in Norway. And we think that by inviting to national and international, preferably the other way around, international and national collaboration, we can bring science forward. I would like to emphasize the need for cooperation through geobiology, example given by deep sea vents, and the science needed to extract and utilize the various marine organisms living in and near these vents. Obviously, there's a huge need for it, both in medicine as well as in other parts of society. There is also an increasing need for seabed mapping. It is astonishing that we normally know more of what's up in space than what's on the seabed. 2004, IMBER, together with a lot of other research institutes, ran the Moderator cruise on the Mid-Atlantic Ridge. The number of new species identified with that cruise alone was impressive. That says a little bit on how little we know about what's in the water, the effect of water, the effect of disease on human life. The government of Norway has put money into establishing a marine biobank, Hofmann, hosted at the Institute of Marine Research in Olsen, where we try to gather samples from organisms from sea bottom and see how they can be utilized scientifically. It's an open bank. Please visit it on our website. I would also like to stress the need to fully understand the effects of the ocean carbon cycle. If you look around the world, we will have an increasing population. There will be a need to feed this population, and the answer is obviously the ocean. Science, utilizing science and sustainable management, sustainable utilization of living marine resources, either synthetic, selfish, or whatever, will be in the future a key to solve the nation's problem. This can only be done through this kind of science, the science we are doing at IMBER, and the challenge is to let the people behind the need for science educate them so they understand the need for science, and that development in a sustainable way in the world can only be met by putting more resources into science, and that the science community are able to utilize the science to a better world for all the population. The answer, ladies and gentlemen, rests on the science. We have two ways, the scientific challenges and also the way to convince the politicians that science is needed as a change, and the present utilization of the world resources also is needed. I wish you all a good conference. I think you give us more science we need. We We have a strong Norwegian representation here, so I will not go through the entire list, but I'm pleased to see that so many scientists have designed to come to the Bergen. I hope I will be able to meet you all again in a more relaxing manner on Thursday during the day. I wish you successful days after that. Thank you very much.
Thank you very much. I will hear from Rector and
Thank you. Good morning, ladies and gentlemen. It's a pleasure to be here this morning to address you during this opening of your conference. So, dear conference participants, it's a great pleasure then to address you during the opening of this conference on the integrated marine biochemistry and ecosystem research. First open conference entitled Future Oceans. What a great title that is. To understand the sensitivity of marine ecosystems to global change, to predict the ocean's response to these changes, as well as the effects on Earth system and human society, as we heard already, is widely required to secure a sustainable future. As you do know, or some of you would know, our Ministry of Research and Higher Education is about to launch a long-term strategic research plan, and one of the items on that agenda is the oceans, the marine research. And I think it's also fair to be said that our deep oceans are highly underexplored. The potential for new species, etc., but also the potential for new insight is just right around the corner if we dare to embark on this endeavor, exploring also the deep oceans to a larger extent. As we heard also from a feeding the world perspective, I think this is absolutely crucial. This conference will hopefully provide a platform to synthesize knowledge of how the natural sciences and human dimensions of global marine change and inform policy and management frameworks to respond to this global change. 2 years ago, MIT launched what they called the third revolution for science. They call it the convergence of science. And that was sort of a new way of working together across the various disciplines, humanities, technologies, etc. included. And I think by addressing such a big topic, important topic as the future oceans, this very way of addressing the complex research questions is the very way to deal with it. So the convergence of various sciences in order to have a broader perspective, understanding of the future of oceans, I think is also in line with your conference ideas and highly appreciated. We are proud that IMBER chose the city of Bergen after the winning bid was submitted by the Institute of Marine Research and the University of Bergen jointly. I think it's more or less true to say that Bergen has amassed a unique combination of expertise and resources within marine and climate research, with more than many outstanding scientists and state-of-the-art research infrastructure, which is so crucial these days, including a fleet of research vessels, labs, field stations, long-term observational data series, computer facilities, etc. Here in Bergen, our researchers collaborate with the management of marine resources and the environment, the industry, public and private sector linked to the marine and maritime issues. This is definitely explained also to our research endeavors. It is of great value to us that you, IMBER, has come today. As a university, we hope this conference will foster scientific friendship, collaborations, discussions to develop the cooperation in order to explore new ideas and opportunities. That is at the end of the day, the very core activities of the university. And therefore it may be also that some of the young scientific visitors perhaps find new friends in Bergen. Who knows? Perhaps they would consider also picking Bergen as the next place to work. I would like to see that happen if possible. So, with that, I wish you the best luck for the conference and hope you have a great day here in Bergen. Thank you.
Thank you very much for your comments. It's a very appropriate start to the IMBER Open Conference. And so the next few minutes, what I'm going to do here is to give a little bit of background on IMBER and why we are all here. So what I want to talk about in this presentation is to give a little bit of a history of IMBER, because sometimes knowing where you come from helps you figure out where you're going to go next. And talk a little bit about what IMBER is, the IMBER science achievements, how we do our science, and the future and the goals of this Open Science Conference and the expectations. Okay, so where did IMBER come from? Where are we? Okay, many of you may remember the Joint Global Ocean Flux Study Experiment, which was an international study throughout the late 1980s, 1990s. And JGOF ended in 2003. And at the same time, there was the Global Ocean Ecosystem Dynamics Program, also an international global change program that was going on. All right, so planning for IMBER began in the late 1990s with a conference in Paris in 2000. And Julie Hall was doing that, who will be here later. And IMBER came along and JGOF ended. And at that point, after the meeting in Paris, IMBER wrote its first science and implementation plan, which was published officially in 2005. GLOBEC as a program ended in 2010. And at that point, many of the programs that were going on through GLOBEC made a transition to IMBER. And at that point, there was an addendum written to the IMBER science plan to accommodate the program from GLOBEC. IMBER doesn't work in isolation. There's a large number of other global environmental change programs, the land ocean in the coastal zone, the LOEC program, the surface ocean lower atmosphere program. Several of these, and these are partners that we have relationships with partners, as well as other international groups such as ICE and ICE. And so all of us working here, and here we are now, 2014. We're at our first Open Science Conference, and IMBER has now been going for about 10 years. So we're at the place where it's time to think about what we have done, what we have accomplished, and where we want to go in the future. The other thing that's going on is that one of the co-sponsors of IMBER, the International Biosphere Program, which is back here, co-sponsors IMBER along with the Scientific Committee for Oceanic Research, or SCORE. The IGBP is going away, and by the end of next year, there will be a transition from the IGBP to another entity called Future Earth. And there will be more about that in the presentations I put in with Friday on Thursday night. All right, so if IMBER continues, it will be potentially with Future Earth, but also with our other co-sponsors, SCORE. So one of the intents of this conference is to think about how we would make the transition to Future Earth and to continue potentially into the future. Okay, so IMBER right now is structured around 4 research themes. These are the interactions between biogeochemical cycles and marine food webs. And this takes a lot of the information or the ideas that were from JGOF, which was the biogeochemistry program, and GLOBEC, which focused on food webs. And with those 2 programs, realize that they have to go together. So that's the primary theme for IMBER. The other is the sensitivity to global change, the feedback into the Earth system, and an important development for IMBER is inclusion of responses to society for the human impact in the marine system. All right, so IMBER is organized in this way. First and foremost we have the IMBER scientists, and then the science is done through regional programs, which I'll talk about here in a moment, topical working groups, national programs, endorsed programs, and through our partner organizations like Pisces and Eileen. All right, all of this is coordinated by a scientific steering committee and also a regional project office at East China Normal University in Shanghai, China. And all of this is overseen by the International Project Office, which is here at the Institute of Marine Research in Bergen. And we also have our sponsor organizations, the IGBP and SPOR. And so IMBER, if you look at it this way, right now IMBER has 4 regional programs, which I'll talk about in just a moment. The working groups are listed here across the bottom, and I should say one of these working groups in Upwelling, being led by Tim Drinkwater, is the joint activity with FlyBar, the Climate Variability Program, which is another international program. So what these are, the CLIOTOP program, Climate Impact from Oceanic Top Predators. This is a program that has looked at improving understanding of changes in the distribution and abundance of pelagic species. It's being led by Alistair Hofmann and Kevin Lee, and both of them are here. The other is Ecosystem Studies of the Subarctic Seas, or ESIS. All right, and this is done a comparative studies to look at across the Arctic seas, to look at climate variability, global change in various aspects of the subarctic seas. It's being led by Tim Drinkwater, Tom Smuter, and Saichi Papa. Also here. Right? The ICE program, the Integrating Climate and Ecosystem Dynamics in the Southern Ocean, is looking at assessments of change and modeling and quantifying food webs and feedbacks into biogeochemical cycles, and Eugene Murphy is leading that program. And then there's FIBER, which is a relatively new program. And I should say that CLIOTOP and ESIS started under GLOBAC, and they made the transition to IMBER. ICE began as a joint IMBER-GLOBAC program, and FIBER is a program that's been developed under IMBER. And FIBER is an Indian Ocean program looking at multidisciplinary research throughout the Indian Ocean, and is putting a lot of effort into biogeochemical measurements. Right, so these are the 4 regional programs for GLOBAC, and we also have working groups. There is a joint SOLOS IMBER, Surface Ocean Lower Atmosphere, which is another global environmental change program. And we have joint working groups with them that look at ocean carbon, various aspects of ocean carbon research. One of them looks at, is a working group on the surface ocean systems. This is being led by Andrew Linton. And they put together the SOCAT Atlas, the Surface Ocean CO2 Atlas. There was a workshop yesterday to talk about next aspects of that. Another working group looks at carbon in the interior ocean, the bluebirds, and they've been looking at instrumentation on Argo plates, the bio-Argo plates. And then finally, there is the Ocean Acidification Working Group being led by Jim Orr, and this group has been successful in contributing to the development of the Ocean Acidification International Coordinating Office, which is at So these working groups have been very active and done quite a bit. There's also a working group on capacity building. This is very important for IMBER because we won't be anywhere in 10 years if we don't build the community that has an interest in IMBER, particularly the early career scientists. And this is being led by Xing Hang from China. There's also a data management working group, which has been part of IMBER since the beginning. This is led by Alberto Villa. One of the products from this group is the IMBER Data Management Cookbook, which there are copies of it on the tables out there, and I encourage you to take one of those. All right, and then the continental margins, this is a joint group with the land-ocean interactions also run Deloitte, also a global change program being led by Casey Wu and Thomas from Deloitte. And this is looking at activities or the science of continental erosion. Okay, and then the final one being led is on human dimensions, human responses, being led by Alida Bundy and Amina Isaac. And this is a new activity, a new approach for IMBER, and we'll hear a whole lot more about that later on in the week. And if you look around at this meeting, they're not just people doing marine science here. We also have people who are interested in social sciences and the interface between human and natural sciences. And that's going to be an important theme as we go through this week. All right, so how does IMBER do its science? Well, IMBER is not a funding agency the way traditional, when you think about traditional funding, but what IMBER does is it provides a coordinating activity and bringing people together through these types of activities like this meeting. All right, and one of these is an Vivo, and we've had 3 of these now. And Vivo is a blue or gathering. So we bring together scientists around particular topics. The last one we had was in India in January 2013. There were 3 concurrent workshops that looked at aspects of continental margins, anthropogenic perturbations to the open ocean, and human-ocean-human interaction. So people spend about a week, talking to each other in small groups, and the intent of this is to come up with some type of synthesis or some product that will provide direction for how the next phase of research should go in these particular. Just to let you know, we're in the process of planning the 4th IMBER for fall 2015, and there'll soon be a request to the community coming out to ask you what the topics are you might want to see covered at this time. The other thing that IMBER does is we've convened summer schools. All right, we've had 4 of these now, although there will be a 4th one in August of this year at East China Normal University in Shanghai. Ingrid Van Puten, Jen Jin, and Stefan Hutton are the co-conveners of this. And the last 2 or 3 summer schools have had a focus on looking at aspects of research at the interface of human and natural systems. And the one that's coming up this year in China will be looking at that as well, looking at indicators that are to evaluate marine systems and human populations and figuring out what indicators are important for policy and management and what the management policy people want in environmental science indicators to make this decision. All right, so IMBER's done a lot. There's lots of special issues, lots of books, lots of products. If you look on the IMBER website, you'll find all these listed. So there is a lot of information that has been gathered, synthesized, and developed through the various activities of the IMBER working groups and regional programs. All right, so what is IMBER? IMBER is a strong research community with a focus on the marine biogeochemical cycles and ecosystems and responses to global change. The project in its first almost 10 years now has made a lot of progress in putting together the biogeochemistry and the physics. It's an integral part of a much larger global environmental change research program. IMBER is one of 8 global environmental change programs that are sponsored or co-sponsored by the International Geosphere Biosphere Program. And also there are other programs through other organizations that are partners with IMBER. We're very open to partnership with other initiatives, as an example, FlyBar and Pisces and ICES. And I think something that IMBER has done very well is to bring together natural and social science communities to study impacts and feedback between marine and human systems. And I say we've done it well because we're one of the first of these groups that has actually tried to do this. And as I said, we'll be hearing more about this later in the week. All right, so what do we have? We have an integrated, interdisciplinary, global environmental change project. We're already trying to connect natural and social sciences, and we're making progress at different spatial scales at local, regional, and global scales. And that's through the working groups and the IMBER regional programs. Okay, but things are changing. All right, IMBER is approaching its 10-year mark, and it's time to reconsider or think about science directions for the next few years. As I said earlier, the co-sponsor, the IGEP, is ending in 2015, and the transition to Future Earth is intended to be complete by sometime in 2015. And what is Future Earth? All right, it is an international research initiative that's designed to develop the knowledge for responding effectively to the risks and the opportunities of global environmental change and for supporting transformation towards global sustainability in the coming decade. All right, that's a lot, but we need to, I think, figure out what they actually are meaning here, and hopefully in Corinne Lazare's presentation on Thursday, will provide some more guidance for that. All right, so IMBER has been invited to join Future Earth, and along with the other core projects of the IGP. Okay. So that brings us to our Future Ocean conference here. All right, and what we're looking at, or what we hope this conference will do, is to highlight and synthesize IMBER science and IMBER achievement, to integrate IMBER science to provide a basis for a science plan or research agenda that will go on into the next decade or so. And the science plan will be, or this plan will be the basis for the request that we use for an extension of this program, and also for our transition to Future Earth, what we expect from Future Earth, what we can provide, and then what we would expect in response to that. All right, a big part of this is community engagement. This is not something that I'm going to do or the IMBER steering committee is going to do. It's something that needs to come from the IMBER community. All right, and the IMBER community, a lot of you are right here at the Open Science Conference. It's the scientists in our regional programs, the working groups, the national programs, regional programs. As we heard earlier, there were about 700 abstracts submitted for this conference. There's something on the order of 140 posters and 320 oral presentations. That's an astounding response we got to the call for this meeting, and it covers such a wide range of topics and expertise. All right, we have about 480 participants here representing 44 countries and 16 developing countries. So it is a cross-section. What we have for this meeting is a nice cross-section of the IMBER science. All right, the 11 workshops and 21 sessions represent IMBER science themes, the activities of the regional programs, and the various interacting groups of people here. All right, so the intent of all of this is to highlight and synthesize IMBER achievements, and from this, pull out the inputs that we'll use for planning the next phase of IMBER research. All right, so what is our way forward? And we'll talk more about this tomorrow, but in the early part of this year, we solicited inputs from our regional programs and our working groups and partner organizations about what had been achieved with IMBER and what new research directions might we want to consider in the future. All right, so that input was collated by the IT International Project Office staff. It was looked at by the organizing committee for this conference and also the IMBER Executive Committee. And hopefully all of you have received a draft position paper that has been developed from this input. And I stress the word draft. It's simply something to get a conversation started. All right? And in that, we outline some of the key scientific issues and challenges relating to the ocean and global environmental change, and how IMBER might want to address these over the next 10 years. All right, and the potential research themes that emerge, I'll talk more about that tomorrow, and those are going to be the focus for breakout groups they will have on Thursday morning, which is the opportunity to provide input and suggestions about the themes that have come out of this or to provide new themes. All right, so the Open Science Conference provides a venue to present the findings from IMBER relevant research and promote integrated synthesis of IMBER research. But it also provides the opportunity for us to update the research agenda to guide our future research in marine biogeochemistry and ecosystem food web, and to focus on the human dimensions of global marine change and the interaction of the two. All right, so this Open Science Conference is a very important mechanism then for us to gather your input and your thoughts about where you want to see IMBER going into the future. All right, so some final comments here are that the environmental issues that we are facing today, particularly those related to global environmental change, are at the interface of the natural and social sciences and humanities. And this is where curiosity-driven science, which many of us do, comes together with problem-driven social science research and the feedback from responses. And I think that's the real challenge for the future, is to figure out how to navigate that interface between the human and natural science. All right, so from what we have done in the past almost 10 years, the IMBER community, I believe, is very well poised to be able to take the lead in this area of research. All right, and I'll just say that I think that's a very important area, and hopefully that will come out of the discussions we have over the next few days. So this type of meeting does not happen, and usually we thank people at the end, but I'm going to start with a thank you. But this type of meeting doesn't happen without the dedication of a lot of individuals. The IMBER Project Office, Lisa Madison, Bernard Apple, and Olsen were they've been just outstanding in doing things. Also, the Regional Project Office in China, Zhu Yu and Zhu have been very good. They've been wonderful about putting things together. I also want to thank the local organizing committee who are listed here. And we mentioned earlier today, we've done a great job of arranging the venue. Also, the conference planner, Kate, has been very good at, done a good job of arranging it so that we can all come and enjoy the lovely city of Bergen. And then the scientific organizing committee for the conference. If you look at the people here, Julie Hall, Wally Wood, Ian Carey, Carol Robinson, and Bernard Alvo. These people are distributed all over the world, and we met on a conference call, virtual meetings at very relatively frequent intervals initially, and that required some people to be awake at 2 o'clock in the morning or to stay up very late at night. So it's an indication of the dedication of these people to do that. We also thank our also we thank our sponsors. Again, this would not have happened, and without the sponsorship and very generous sponsorship from the organizations and groups who are listed here. And we thank them to see them around. And then also, we always thank our sponsors, our co-sponsors, SCORE and the IGBP, because without them, IMBER would not be here as a project. All right, so if you're having fun here, you see something you like, please tweet about it. And this is the handle or the name to use it. So please tell other people about what we're doing here. And let the community know. But as we go through this, if you hear something you like, please tell others about it. All right? So at that, I will stop at that point, and I think I have time for a question. Okay. And if there are a couple of questions, and then we'll move on to the first of our several plenary sessions. And I should say the plenary sessions will be in this room in the morning. And then during morning coffee, this room will be then split back into smaller rooms for the concurrent sessions in town following morning coffee break. Okay, so hopefully, I'll just take a couple of questions if you're on. Okay. Let's see. Okay, so while Bernard is
We'll just give a little bit of, we've got a question there.
yeah, question.
I'm sorry, just a technical point. When our comments on the
Oh, okay. Tomorrow, okay, I guess that's tomorrow, but anytime there has been a survey set up, a survey monkey set up so that you can actually go to the website and enter your comments on that. And I would request, I'll provide more information on that tomorrow, but I request that you do that and sooner is better. And please, any and all comments. All right, so we're a little bit ahead of schedule, but I think we'll go ahead here. Okay.
Give us more time for questions.
All right, so it's my pleasure to introduce Julie Hall, who will be the moderator for our first plenary session this morning. And Julie is the past chair of the IMBER Scientific Steering Committee, and she was involved in developing and setting up what has now become IMBER. Julie is at the National Institute for Water and Atmospheric Research, and she's going to moderate our first session.
Thank you, Eileen. And it's great to be here. And what I think from the beginning of IMBER to now is to see such a broad community here and to see so many new faces, to see the IMBER community growing and the breadth of research, particularly bringing in the human connections research. I think it's a very, very exciting time for IMBER in terms of looking at the next 10 years of research. So each morning we have plenaries to start the day. And today we're going to have two plenary presentations. The first by Nikki Gruber. Nikki, as you saw from Eileen, is chair of the Ocean Carbon Interior Working Group that's joined with IMBER and SOLAR. Nikki is from ETH, from Zurich, and Nikki, we'll hand over to you.
Good morning, everybody. It's a wonderful pleasure and honor to actually start the scientific program. I would like to thank the organizing committee for putting together this wonderful conference and also giving me the opportunity to talk this morning to you about a topic which has grown and come very close to my heart. But at the same time, I have to admit that whenever I talk about ocean acidification and changes in the oxygen content in the ocean, I sometimes feel a little bit the prophet of the doomsday. And I hope I won't leave that impression. But I would like to highlight the fact that a lot of changes are on the way at the moment in the ocean, and particularly at the regional scale. And it's one of the most important findings, in my personal opinion, of the recently terminated AR5 process upon PCC, is the conclusion that global change is not something that happens in the future. Global change is happening already. And we're seeing the impact of global change already across many fields. In the freshwater community, I think these things have well as being established. I think the marine community, we're still struggling essentially with sort of this very concept. And to a very large degree, this is a consequence of our lack of observations. We have very few long-term observations in the ocean that provides us a basis for assessing the impact of global change on marine ecosystems, on marine biogeochemistry. And so what I will be presenting today is not going to be based on observation, it's going to be based on models alone. So why I'm putting up this animal here, this theropod in the ocean. And the big question that I would like to pose today, is this animal, sort of the canary bird, that of ocean acidification or changes in the ocean? And the answer, I don't know. I'm not able to tell you today whether this is the canary bird or not. But I will be able to show you today that the biogeochemical changes are happening and they will have an impact, I'm sure. But what the impact is going to be, I think this will require a research effort at the scale of IMBER and even beyond to address this very question. I think we're just at the beginning of being able to address this issue. And it's not just only ocean acidification, it's the other changes as well that all acting together. Global warming, changes in circulation driven by this warming, all the changes in wind patterns, and also the consequences those changes might have on oxygen. And all of those things working together on marine ecosystems and marine biochemical cycles. This is a key topic, I think, that will be with us in the coming decade. What I'd like to show you today is not so much the global perspective, but really the regional perspective. And I also have to admit, I will be focusing primarily on one single system, and that's the California current system, because that, on the one hand, is probably the best observed system of all these eastern boundary upwelling systems, but also the one we have done most research on. I will also now talk about, in extensio, about the warming impact of changes in oxygen. There are very important topics as well, but I'll focus on ocean acidification. Much of what I'll be presenting this morning is based on really wonderful collaborative work of people in my research group. I would like to thank particularly Zure Lockhart, Matt Munich, Franklin Oveda, Thomas Ehrliche, and Julian Latour, and many others that have helped through the years to look at this issue. So what particular topics I'll be talking about, first I would like to bring home the message that when we look at the impact of these global stressors, we have to go at the regional level. Second, I would like to show that a lot of these changes are really on the way at the moment, and in many ways that actually provide a wonderful setting for looking at impacts on the marine ecosystem and biogeochemistry. And then I would like to stress in particular that we don't need to look just how things are changing through on the long term, but there's a lot of variability included, and this variability goes in both ways. It goes towards more favorable conditions, but also goes towards less favorable conditions. And these extreme events is one issue that we haven't well observed, nor have we addressed them very well without our modeling activities. And then, lastly, I would like to go a little bit beyond the California current system and also beyond ocean acidification. So, looking back in time, when we started to work on ocean acidification, so our perspective was, this is a global stressor, we're increasing atmospheric CO2 concentration, that CO2 will enter the ocean and lead to acidification. And since this is atmospheric CO2, is more or less from an oceanic perspective equally distributed everywhere in the atmosphere at the same concentration roughly everywhere, that the ocean everywhere will be kind of changing the same way. And if you look at these model-based simulations of how the ocean pH looks through time, this is very much the impression that you get, sort of the whole ocean is changing in a similar way, and all the pH is going down from top left 1875 reconstruction for the pre-industrial period going into the end of the century at the bottom line. So the colors are just changing uniformly. And it was through research done on the modeling side, which, for example, Jim Orr's paper that mentioned, for example, that The Southern Ocean will be among the first regions to enter under saturation, later by Martha Steinhofer and others, who showed that the Arctic Ocean is also one of those areas where you see changes first. But it was then observations that really took that message home that not the whole ocean is the same everywhere. And it was particularly this paper by Dick Feely and colleagues where they looked at the carbonate ion distribution and expressed here in terms of the saturation state, and particularly the border between the upper ocean, which is supersaturated, and the deeper ocean, which is undersaturated, this horizon of saturation with regard to aragonite. When they started to map this out along the coast of California, they showed that this separation between under and supersaturated condition is showing very, very close to the surface as we approach the continent. And this means that organisms that live in these very rich ecosystems are exposed regularly to undersaturated conditions. And regularly doesn't mean at this point in time it was kind of one-point survey. There was no information how this has changed through time or how frequently such conditions can appear. And it was particularly, for example, up here when they had strong upwelling with the summer cruise off the coast of Northern California and Southern Oregon, where the saturation state showed us shallow at about 40 meters. That was really a source of concern. But other work in the California current system has also pointed towards the impact of other drivers, other stressors. Here's some work by Steve Borgrad and colleagues on the top left that showed how the zone of hypoxia is showing, so that the depth where you reach 60 micromolar of oxygen has been showing towards the upper ocean. And also recent sort of research where people looked at observation and were able to show that a lot of eastern boundary upwelling systems, such as the California current system, have recently done changes towards stronger upwelling, as expressed also in hydrochlorophyll concentration. So all of those together really form a triumvirate or even quadrumvirate, many, many stressors that act upon the ecosystem. And what that means for marine biochemistry and marine ecosystems, at the moment, it's not very well established. And I won't even try to give you sort of a summary assessment at this point in time. But what I can do this morning is to provide you sort of the biochemical, physical context, the carpet, the variability that will act upon the ecosystem biochemical side. And I'm particularly going to be stressing the spatiotemporal dynamics of these. It's not just the mean change, it's change with regard to many aspects of the system. Okay, so the first thing I would like to do is to take a look a little bit into the future. As I said, the primary tool we're using here is models, and we're using here regional models. And the big advantage of using regional models is that we can address these issues at high spatial resolution. And I just illustrate the advantage of going to high spatial resolution with a series of images, which shows a snapshot of the surface ocean pH as modeled by different types of models. On the top left is the type of resolution you typically have in world, the models that span the whole world that are being used for the IGDP type assessments. So the border of 300 kilometers nowadays may be more than 100 kilometers resolution. Then if you go towards sort of the current version of the highest resolution we have more or less on the globe, then we're approaching about 60 kilometers. And you see this on the top right. You start to see sort of the emergence of low pH conditions along the coast of California. But it's only when we go towards 15 kilometers or even 5 kilometers we start to see essentially the spatial structure of the upwelling and the corresponding impact on the surface ocean pH. So I'll be using for everything in my talk models of resolution of 5 kilometers. The type of ecosystem model and biochemical model we're using is relatively simple. It's a model that has a single phytoplankton functional group based on the phytoplankton middle. It's limited by a single nutrient type, in this case nitrogen, which also supports nitrate and ammonium. It is a little bit more complex in the sense that it has two tidal pools that interact with each other. They're coagulating, also coagulating phytoplankton, and everything, and the phytoplankton is eaten by a single zooplankton. You see, from an ecosystem point of view, that's about as easy or a simple ecosystem model that you can imagine. But it's sufficient, I think, for addressing most of the questions I will be talking about today. And this is coupled to a marine biochemical model that includes carbon, oxygen, and all the relevant carbonate species needed for a proper modeling of the ocean carbon cycle. When looking at the impact of climate change on such a marine ecosystem, then there are different ways how you can approach it. And the particular approach we have taken here is not to go at full complexity. And then to illustrate that complexity, I sort of drew here essentially the three dimensions of these potential stresses. On the going to the right, you see the changes in atmospheric CO2 going in the vertical direction. There's a change in circulation that we sort of mimic by changing the wind stress or changing the upwelling, and then going into the plane is the global warming. And if you were to force essentially such a model with the full complexity of climate change, then you would have a very complicated trajectory within that dimension. And we say, okay, well, this is too complex at the moment, but rather focus on a much more simple approach and just look largely in one dimension, which is essentially the CO2 dimension. So changing atmospheric CO2, we do this in two ways. One is just essentially constant climate forcing, and also now more recently we added a simulation where we include the full climate variability, what we call a handicap, which starts to go a little bit into this three-dimensional space. So now I have to make sure. Just to give you an illustration of what such a simulation can do and what it cannot do, I show you here a simulation that goes from 2005 into the year 2050. On the left-hand side is the depths of the saturation horizon. On the right-hand side is the surface ocean pH. And as you can see that, if you focus first on the left-hand side of the saturation depths, that at the beginning the saturation depth was more sort of in bluish color, sort of on depths on the scale of 200, 300 meters. And if you go towards the end of the simulation, we're approaching that 2040, 50, you see that we go into the reddish color. So we see essentially the shoaling of this saturation horizon very close to the surface. And at the end of the simulation, we have typically depths on the order of 20 to 30 meters. So the layer where we have super saturated conditions remain going to be very shallow at the top. You also see the pH by that time has sort of been reduced about 7.8 units. The other element that is, of course, striking if you look start the simulation again is the spatial and temporal variability. I mean, not the whole system is kind of moving in similar fashion, but superimposed on this we have dramatic changes in space and time. And it's the organism, the ecosystem will experience not at the situation at one location in one time, so it will be exposed to all of that variability, not as a new explanation into the future. So I think this variability, I believe, is as important as the change in the moon. Okay, so, but nevertheless, let's focus a little bit on the mean changes. The first thing I'll show you here is the change in the surface ocean pH. On average, it goes just a reduction, roughly from about 8.2 at the beginning, or 8.15 in the nearshore areas, going to about 7.9 in 2050. But sort of probably more important for organisms, at least my personal opinion, is the change in the saturation state with regard to aragonite. So in pre-industrial times, I should indicate the saturation depth with the white line. Is located about 300 meters, and as we go towards the present, we have sold already by about 100 meters or so, and if you go into the future, you see this dramatic shoaling even deep into the Euphrates zone. And what that means for ecosystems is that the habitable zone for those organisms that are sensitive to the saturation state are becoming smaller and smaller. And the way I try to illustrate that is that I combine now the simulation that goes into the future, which is shown on the right-hand side, with a hindcast simulation we have recently done that covers the period 1979 to 2010, and I pasted them together. And color-coded in such a way that if it's dark blue, then the saturation state is about 2. Then we go to the light blue, it's 1.5 to 2. Then yellow is 1 to 1.5, and red is undersaturated conditions. And shown is the volume of water in the near short 10 kilometers in the upper 60 meters. And so you see the variability as it goes through time, but you also see essentially the disappearance of waters above saturation state 2, and you see the appearance now of regular conditions where the saturation state is below 1. And by the end of, by 2050, half of the volume in that 10 kilometer zone in the top 60 meters will be undersaturated. And the other half maybe just between 1 and 1.5. And in terms of sensitivity, I mean, it will depend now on whether or not organisms are sensitive or not, how they will be coping with those conditions. But the point I'd like to draw your attention to, that we're actually at the moment sort of an interesting transition phase, because the appearance of undersaturated conditions, if you believe our model result, is actually a recent phenomenon. Only started maybe about 10 years ago. But you see that as we go into the future, by 2020, it's becoming a 20 to 30% occurrence. So we're just at the brink now of major changes, at least in this particular system. You go deeper in the water column, you go to 60, 120 meters, where we see also this transition in the coming decades. So at the moment, we're at 1 to 1.5, still supersaturated most of the time, but within 10 years, undersaturated conditions will be the norm. And if you go to the bottom of the benthic layer, already today it's on average very low, but it becomes essentially permanently undersaturated. So, what does it mean now for marine ecosystems? And coming back now to the Plenary in the gold mine, because there's recent work by Nepstad and colleagues where they looked at one organisms and this pteropod, and they looked at whether there is some indication of shell dissolution in their natural habitat. So they collected these organisms along the cruise and tried to relate sort of indications of corrosion on the shells with in the context of the environment they're living in. And they came up essentially based on these observations with sort of an impact chart, which shows on the vertical axis the number of affected individuals versus the percentage of undersaturated waters. And you see that undersaturated conditions are rare. You see very few of these organisms. And if you move towards more permanent undersaturated conditions, you see the majority of organisms show this indication of corrosion. Now, if I put now our projections onto this chart, then you see that in the year 2000, we're sort of on the left-hand side, we have sort of 10 to 20% of the time with undersaturated conditions. But by 2050, both the upper 60 meters as well as the 60 to 120 meters, we're going to be in this 80 to 100. But this organism will show significant corrosion signatures in the future. Well, it doesn't mean that this organism is going to die, but what it means, at least that's my personal judgment now, is that this organism will have to put in additional resources, more energy for fixing this problem, and will have less energy for reproduction, for growth, and to do other things. And other organisms will be similarly impacted. And I think it's up to this research community to really think about how these biochemical changes that we're modeling will affect marine ecosystems. Okay, now talking a little bit more about sort of not changing in mean, but changes in extreme events. So I showed you the variability, and here I'm just plotting this sort of like a probability density function. So x-axis pH or omega saturation state, and on the y-axis just the relative frequency of these particular states. And now when we think in terms of extreme events, we can there's two ways how you can identify an extreme event. One is that you kind of fix a threshold where you say, well, if conditions go below X, then we have a problem. Another possibility is that you say, well, I define the threshold at some percentile. We pick here, for example, 1 percentile. So these are conditions that occur rarely, and organisms might not be particularly adapted to cope with those conditions. I call them type 1 or type 2 thresholds. However, I'm going to show primarily so-called type 2 thresholds in this particular case where we looked at unsaturated conditions. And as we progress, one of the important things to remember, as we progress towards lower and lower states, without even widening distribution or changing, the number of these extreme events changes non-linearly, as there's a linear change essentially of the overall condition. So we see a dramatic increase. In a particular way, we're going to be looking at such extreme events is we look at an index that we call severity. And the severity of an event, this is concepts that are also applied in droughts and heat wave research on the impact on the terrestrial ecosystem. The severity is the product of the intensity, is how strong the event is, and duration, kind of integral on the curve below the threshold. So let's take a look at how intensity is changing through time. Here, essentially the 10 kilometer strip along the coast of the US West Coast. So the mean intensity is very low, 1.05 perhaps right now. But as we go into the future by 2050, we are going to these regular undersaturated conditions, and we're undersaturated in the mean by 0.35. So the omega would mean 0.65. What does it mean now in terms of the severity? So you multiply this now by the duration, and we're looking at this as a somewhat more complicated graph. I would like just to focus first on the left-hand side and on the line. So this is the cumulative frequency, the distribution of these of the severity, product of intensity and duration. So right now we have these are very rare events in 2010. It's the yellow curve. So we may have the severity on the order maybe of 10 or so. By 2030, the median severity is already on the order of 100 days. And by 2050, we're going to 500 days. So that means 500 days is an undersaturation of 1, or 1,000 days is an undersaturation of 0.5. So this is really at the threshold of the severity being sort of a rare something, becoming sort of a very common situation. And when you look, for example, at this also as a function of different thresholds, so on the right-hand side, we plotted the number of the mean severity as a function of different thresholds. So if the threshold is at the higher level, 1.4, then already today this is a rather common thing. The threshold is 1.2, then it's sort of, we're just at the brink, and if the threshold is 1, then we're just at this transition at this very point in time. Okay, so the last thing I would like to mention is that now looking beyond the California current system. So is this something we have to worry also elsewhere? So we've done similar exercises, similar modeling setups at very high resolution, in this case 5 or 7 kilometers for the Canary current system and the Hubble current system. At the top, and what we're showing here is the omega in the 30 to 60 meter range. And what we see in the Canary current system is that although the system is going to go towards lower saturation state, it will not reach unsaturated conditions. This is largely a result of the different chemistry of the Atlantic Ocean. It's much more alkaline ocean than the Pacific, so it's better buffered against the changes. Not true for the Hubble current system. So 1750, 2000, 2050, you see the appearance of blue colors. So the Hubble current system, as a matter of fact, has already proceeded beyond the California system. Its average saturation state is lower than that of the California. That means that transition is already occurring right now. And I'll show you just a snapshot of our modeled omega saturation state for the Hubble current system of Peru. And we modeled that in the wintertime, undersaturated conditions in that region are almost getting to the north. And I would like to see observations to challenge essentially our model prediction at this point in time. But it certainly points that this system is also very sensitive. And now, the very last slide that I would like to show here is now going beyond ocean acidification. And so there are other stressors that we have to worry about. And as I said, we've taken here sort of the approach of doing just idealized simulations where we either change, for example, the warming, going into the plains, or the vertical, changing the wind stress, so to mimic ocean circulation changes. And what I can tell you is that the story is not as simple as we had thought. The first idea was, well, if you increase the wind stress, then we're going to accelerate essentially ocean acidification because you increase the upwelling of corrosive water from below. And if you look at the top left, in terms of the California current system, this is exactly what happens. So if you increase the wind, going to the right, as on the left, top left, if you increase the wind in the California current system, the volume of unsaturated waters indeed increases. But what's very, very puzzling when we looked at the response of the Canary current system, there we actually saw a decrease, so not as expected. And Rune has published a paper early this year where he goes into all the details to explain why this is happening. In essence, it is really a balance between the ocean circulation, the response of ocean biology to these changes, because ocean productivity does not change linearly with wind stress, and changes in the surface, in the residence time of the upward waters that lead essentially to these changes in volume. And the same is true, for example, if you look at the response to ocean warming. So the California current system is actually helpful for ocean acidification, whereas the Canary system, we see no response. And some early simulation we have in the Humboldt also show very complex behavior. So I think this is something we still have to explore and further investigate. I will talk on Thursday, we'll talk a little bit in terms of oxygen. The same is true, indeed, for oxygen here as well. So, for example, the volume of hypoxic water in the Canary current system also decreases with upwelling increase. Whereas, for example, in the California current, it's more the traditional sort of perspective. If you increase upwelling, you actually increase the amount of hypoxia. So that means when we look at this now, when we try to make prediction of how these systems respond to all the stressors together, then at the moment I don't think we're in a position yet to make very firm projections beyond sort of the ocean acidification story. But I'll leave it at that. Good. So let me close and start on the first point is that eastern boundary upwelling systems are hotspot of change. And one of the important findings of our research has been that changes that we're seeing right now are are reflecting of imminent changes of substantial thresholds that are being crossed as we go into the future. The second point is that it's not just a change in the mean conditions, but also a change in the variability in the extreme events. And I believe that it's particularly those extreme events that will sort of have strongest impact on ecosystems. Yet our ability to model them and our ability to observe them is not well established. And the third point is that, it's also my personal opinion, that these regions really provide wonderful test beds to analyze the conditions on the biochemical side as they are developing, but also provide the opportunity to look at the ecosystems, the organisms in the ecosystem, and see how they cope with these changes and how they have coped with the changes that have already occurred. But as I said, at the moment, our ability to make some prediction of how these changes are impacting marine organisms is not well established. And I'm not able to go beyond essentially just looking at this table that was put together by IPCC in Working Group 2 to try to assess how, in this context, ocean acidification will have impacted different marine organisms. And I just color-coded them in terms of red being vulnerable and green sort of not being affected. And I just checkmarked those organisms that are also important or at least present in these boundary upwelling systems. You see most of them are present, and we see a fair number of organisms that are potentially vulnerable. But vulnerability doesn't mean that they will disappear or anything. It just means that we will be seeing important ecosystem change. And that's the one thing I'm quite certain about. Thank you very much.
Yeah, we have time for a couple of questions.
Very nice presentation. Could you tell us a little bit about how these changes that are occurring off the California current system are comparable or faster than the Antarctic? How does that work out?
I think in terms of speed, the speed at which, for example, just the pH is changing, that's largely determined by just the atmospheric system. I don't expect to see sort of major and sort of changes in the slope of change. That means that the change in pH could change of atmospheric CO2. Now, in terms of the transitioning towards when critical thresholds are being crossed, I'm not really in a good position to make a comparative analysis because I don't think we have done the really comparative modeling studies in the Arctic Ocean to look sort of more at the fine resolution in time and space to make a direct comparison. But I would argue, I mean, based on what we know already from the Arctic, it's certainly also a region that we need to worry about. But I cannot make sort of say, well, it's worse or better. Another.
Thanks very much. Your focus on thresholds, is that well justified? I mean, most of the organisms, they have organic coatings, they can probably cope with their current environment, whether they're still around. Or is it more the speed of change? So, right now, our politicians might say, canary count is not, it's no problem, it's safe, it's far away from the threshold. But the change is still pretty rapid, so we may have to look at this with respect to the evolution or the change of evolution chemistry rather than thresholds. Do you think what's the best or safest approach not to make give wrong indications for policy?
It's a wonderful question, and wonderful questions are very hard to answer. The reason why I focused on the omega equals 1 threshold is because there's unambiguous evidence that once you cross that threshold, a calcium carbonate shell starts to dissolve. And of course, organisms might have developed capabilities to protect, like diatoms can build their shells in undersaturated conditions, so it doesn't, organisms can't cope with that. But it just means that the investment for that protection will sort of substantially increase relative to the saturated conditions. Now, I emphasize sort of this absolute threshold. I mean, going back to the question of other thresholds, I mean, we've been looking at now also at this 1% threshold. So where you say, okay, organisms have kind of adapted to live in their environment, and if you're like a tree growing here in Bergen, then let's say a temperature of 30 degrees is extremely hot for them, it's 1% event, whereas a tree living in Italy at 30 degrees is a common thing. So the organism has to adapt locally to those conditions. And what we see, of course, also when we look at the 1% change, we're going to be seeing large changes in the occurrence of these events. Now, whether we have to worry about just the appearance of these events or how fast they appear, I wish I had the answer. And I think this is, again, one of the key questions that are arising again and again. How fast, first of all, can organisms adapt to changing conditions? And secondly, how fast can they adapt? Is it just phenotypics? Genotypically, we need, are we seeing species replacements, completely changing ecosystem structure, or are we seeing the same species but different phenotypes of the same species? I think those are exactly the types of questions that an IMBER type of community needs to address.
One final question.
Thank you for the talk. I had a question actually to your modeling approach. I mean, I think you convincingly showed, at least to me, that when you use sort of the 100-kilometer model systems, you don't have any chance to resolve any of the upper dynamic systems. And then when we look at the very high solution that you presented, I think in terms of resilience or questions that we ask here, it's very visible. You can sort of see that indeed we have extreme events showing up early, but they become more sort of frequent as we go forward. But it wasn't clear to me whether the response was actually any different in the high resolution model to that than we would have had with a certain non-result in the low resolution model, because it all looked very linear to me. Although, yes, it has a rich band, it's on the high resolution. Maybe you can comment on whether there's extra gain if you go through the effort of doing high resolution on the signal, other than showing that indeed we have a lot of spectrum of variability even today, and that will be just slowly shifting.
I think the gain, number one, is a much better description of the variance of the system, which is very hard to, I mean, if we knew the variance of the system from observations, then it's kind of safe to for the time being to project that variance into the future as making assumptions it's not changing. And our model has little indication of really changing variance. A little bit, but no, this is not the major signal. So in that sense, a sort of the downscaling approach from the global model using observed variance and use that, I think that would work. The number two gain is the spatial dynamic. And it's not something I have sort of emphasized that much, but one of different places are indeed changing somewhat differently because for example, the eddy field in a place like the California Crust system is not random, it's organized by filament and structure. So you start to see places where you see essentially changes much earlier than other places. And that has again perhaps implications for the marine ecosystem because you might have spots of where conditions are more favorable for a longer time and they can provide holding patterns for, let's say, fisheries, fish spawning, it might be holdout for them that they can survive in that region for a long period relative to places where the changes and conditions occur early in the time. And that's again an advantage that we can provide from the high resolution model.
I know there's a lot more questions, but Nikki's going to be here for the rest of the week.
I have
So please catch them during coffee breaks and things. And I'd like to just take this opportunity to thank you again for the time and effort you put in. And
thank you.
I'd now like to welcome KK Wu. He's from the National Central University in Taiwan. KK has had a long involvement with IMBER and has been the chair of our content marketing task team.
Okay, thank you very much, Julie. It is my privilege here to present Bergen impact on biochemical processes and ecosystems in continental margins, lessons learned from cases around the globe and future perspectives. On behalf of Continental Margin Working Group, you can see here, working group, well, if you want to know the membership, you just Google it. And it represents a linkage between LOICs on the landward side and IMBER on the seaward side. So we're trying to bring ocean closer to people, closer to the shore. Okay, so what is a continental margin? What's the difference between a continental margin and a continental shelf? Okay, we can define it. It is the interface zone between land and ocean, which is dominated by processes arising from the existence of the land-ocean boundary. So, of course, they include shelves, boundary current systems. Well, if just a continental shelf, boundary current systems will not be included. Marginal seas, estuaries, wetlands, coastal plains, watersheds. So it's very broad. But why should we worry so much about it? Okay, so these are the types of continental margins, including the coastal zones, estuary, continental shelf, boundary current systems, marginal seas. Well, because they represent a very important part of the Earth system. Okay, for instance, the coastal ecosystem goods and services comprise 77% of the total economic value of global ecosystem goods and services. Okay, to give you a few examples, more than 90% of fish catch and fish farming are from margins. They are especially rich in biodiversity. For instance, in coral reefs, they represent less than 1% of global area, but account for more than 25% in biodiversity. Margin carbon pump responsible for more than 10% of anthropogenic CO2 sink. It was thought a CO2 source before. And also, one interesting point is removal of fixed nitrogen at a rate of current European price, €8 per kilogram of nitrogen, where the total nitrogen removal on current markets account for about $2.3 trillion US. That's almost the same as the 2012 US budget. Of course, the US budget is not all earned by the US government, there's a big deficit there. Okay, so I think I can convince you that the current margins are very important in terms of providing ecosystem services. Okay, but they are experiencing quadruple squeeze from population growth, development, intensification, rising demands for energy, intensive resources. You can say a new gold rush is on. I'll give you some examples later. Ecosystem degradation loss, especially acute current margins, rising CO2, well, as Nikki demonstrated, very acute current margins. They are not only enhanced by volume, but also by eutrophication. Okay, that will bring more people into the picture. And ecosystem tipping points and rapid and irreversible changes in socio-ecological systems and the societal responses. I will also give you one example. Okay, so I think this is a very good illustration of the rising demands for energy-intensive resources. This shows the increasing maximum water depth of offshore drilling in the Gulf of Mexico. So starting from the 50s, start to drill, then get deeper and deeper in the 90s. They are reaching 2,000 meters, and then in the 2000s, they reached 3,000 meters in maximum depth of drilling. Of course, this kind of endeavor, well, led to the catastrophe of Deepwater Horizon, which is owned by Atlantic Ocean and leads to British Petroleum, caught fire. Everybody knows that on April 20th, 2010, after an explosion in Spain. Okay, so that led to severe ecosystem degradation loss. So I think it's very difficult to estimate how much this catastrophe cost in terms of total ecosystem services and goods. But BP paid the $42 billion US. I think that is some indication of the kind of loss caused by this kind of endeavor. And also, alternative markets appears to be more sensitive to rising CO2. Okay, so compared to the atmospheric CO2 increase observed at Mauna Loa at a rate of about 2 ppm per year, for the Japanese Sea, the rising rate, the increased rate is about 2.7, and for the South China Sea, it's even higher, like 3.2 ppm per year. That's about 60% over the globe, at least the Mauna Loa average. And then, as I said, I'll give you one example of a tipping point. That's okay, given for the change, the drastic change in the Baltic Sea in the 90s. That's due to human-induced nuclear regime shift. Okay, this is the Baltic Sea, and or high sea receives discharge from the yellow sea. And from the 60s to 80s, you can see the dissolved inorganic nitrogen load increase, or at least concentration increase almost linearly, and up to the 1990s. And the dissolved inorganic phosphorus decreased in concentration, and so did the dissolved silicate concentration. And that led to a very severe misbalance of nutrient elements. You can see the nitrogen to phosphorus ratio increased from about 3 to about 14, and the silicate to nitrogen ratio changed from about 10 to about 2, and that led to a change of contribution of nitrogen to the phytoplankton assemblage. So the nitrogen to dinoflagellate ratio dropped from about 50 to about 5. Well, then something nonlinear happened, and so in the late 1990s, the fisheries collapsed. I think that's one tipping point. That whole system did not really recover from that. I think now it's recovering very slowly. Okay, so we summarize the different stressors on common margins, ranging from local to regional to global. So starting from land use change, also damming, dikeing, water diversion, and also discharge of anthropogenic nutrients all come from the land. Then invasion of alien species, and then energy and mineral extractions from the sea disturb the ecosystem tremendously, also overfishing. Then on a much larger scale, the change in water cycle, the rising sea level, warming, climate change, and population all affect common margins. So I'll give you a few examples of how these impacts are and what the prospect in the future. Okay, so anthropogenic nitrogen fixation, we all know that ever since Haber-Bosch process brought nitrogen fixation to human society, there's an ever-increasing amount of nitrogen fixation on land. Okay, so this is the global production of nitrogen fixation on land, starting from the 50s, very low, then some hiatus in the 80s, 90s, then started to rise again. Actually, a few years back, there was some hope that this trend will start to level off, but actually it's not. I think projection from FAO is still going strong. And most recent estimate from Rector in his Royal Society Proceedings paper to report this actually they thought the natural nitrogen fixation on land has been crushed in the 70s. So the man-made nitrogen fixation on land is double that, or more than double that of the natural process. So in response to that, we also see increasing river loads of nitrogen. And this is an example from the Yangtze. Okay, so from the 70s, there's a threefold increase of the nitrogen load. So what does this lead to? Okay, so there has been a summary of the hypoxic zones of the Yangtze River. Reported in 2011. So 2 and 0 reported. So here, throughout different years, for instance, in 2006, very large area of hypoxia. Also in 1999, 1998, 2003. So in short, this is a very
it's an epidemic of this spreading hypoxic zone. So we, well, naturally will ask, is hypoxia in East Tennessee caused by nephrogenic nutrients? So we did a numerical experiment using a rather simple model. Then we used the three-dimensional model to simulate. Well, it's quite difficult to simulate oxygen and all that. So I think that at this stage, we just examine the sediment oxygen consumption. So we compared specific year, 1999, summer in 1999. So the gray areas are observed hypoxic zones, or should be 2011, and reported by Rune. And these are the black contours represent the model results. So I think it's a reasonable agreement that when we drive the model with ever-increasing nitrogen load, building lead to this very intensified oxygen consumption at the water sediment interface. Okay, so I think we can take that. So these hypoxia, hypoxic zones are the result from the ever-increasing anthropogenic nutrients. Okay, so I think that has been long reported that in the 70s there are only dozens of hypoxic events reported, but in the 2000s there are hundreds of them. So I think probably you're all familiar with this report by Diaz and Rosenberg, 2008 in Science. You can see this exponential increase of dead zone reports or events. Okay, so eutrophication not only brings down oxygen, but also brings down pH. And this is one example from the East China Sea and the Yellow Sea. Okay, so the horizontal axis represents the total dissolved inorganic carbon, and the vertical axis represents the arachidonic saturation. And so all these dots represent the samples taken from the bottom water of the East China Sea, and these crosses represent the mean value and standard deviation of those observed in the Yellow Sea. So the lowest value found was in the Yellow Sea in autumn. No autumn observation was done in the East China Sea, so in East China Sea could be as low as the Yellow Sea in autumn, because in autumn that is before the overturn on the shelf and the highest accumulation of CO2 from degradation of organic matter induced by this anthropogenic nutrients. So I think these synergistic effects are very strong on thermal molecules. So I think the worrying reason thing is that this region is a very important region for aquaculture in China, and if the water really goes into undersaturation, I think a lot of aquaculture of shellfish will just diminish. Okay, so facing all these problems, so what should we do? I think we should rethink the engagement at arenas for future continental marine research. So we have come up with 3 important cornerstones for this future continental marine research in terms of engagement events. So first is knowledge and understanding. The second is development, innovation, and the risk. The third is governance. So I will go over each of these things. So for knowledge and understanding, in the past we probably focused a lot on the natural properties, but now we need to make properties in continental shelves mostly, or maybe on the slope. But now we need to worry about not just what's going on
on the margin, but actually it's headwater. Okay, so that's from the watersheds because its nutrients all come from watersheds, not just emerge from it itself on the margin. So we need to engage watershed management in order to really regulate the nutrient discharge. I think that there has been a successful story or history in Europe. So from watershed to coastal ocean processes, and also from ecosystem functioning to societal values. Okay, it really rests on the societal value of how we cherish ecosystem functioning and how we should cut back our easy way of producing things. So I think we need to understand the human mind, and also we need to understand from exploitable resources to governance arrangements. In many places, in many areas, especially on the slope, it's perhaps even out of the EPZ, but they definitely have a strong impact on the Earth system, and there's a lack of governance arrangement there. So we need to engage in these aspects related to the margins. Then development, innovation, and risk. This is a wonderful picture for a wind farm, a huge, massive wind farm in the North Sea of Denmark. I've never seen this before. You can see this is, I don't know, haze, perhaps caused by these windmills. Will they have any impact on the environment? I don't think anybody knows about it. And so because of, it was thought wind energy is such, green energy is such an attractive renewable energy, so there's exponential growth, especially in European seas. So you can see in the European seas, there's exponential growth in wind power installments, especially in the North Sea. So I think with this kind of like explosive development of windmills all over the European waters, what may happen? So there's acute competition for space among wind farming, shipping, fisheries, and other sectors. Well, for instance, more than 50% of sole catches in the German North Sea come from areas for which wind farms are planned. So who's going to judge who should get the right to do fishing or do windmill farming, or they can coexist? I don't know. So the consequences of Northeast environmental status are uncertain, according to Eileen, who's sitting right there. I think these problems deserve careful examination to assess the potential risks. So with development, there must be very careful assessment of risks. Then finally, governance. So perhaps you have heard of this, Alibaba case. This is what Russian minister said. Well, after the Russians submit a petition to UN, so the UN subcommittee has agreed with the arguments presented by Russia and has tentatively declared that 52,000 square kilometers of the Sea of Hawk is part of the country's continental shelf. So this area is a roughly area of Holland and Belgium combined. So not a huge area, but it's the start of the process of the gold rush. Well, the Natural Resources and Environment Ministry of Russia describes the enclave as the real Alibaba cave because it has plentiful precious minerals and natural resources. Once approved, the area will be considered an inland sea. So nobody can say anything about it except the Russians themselves. Well, this is only the tip of the iceberg. Actually, you can see an explosion of claims on extended shelves in the last 10 years. So this is only one case. There are, well, at least according to this plot, 60 others somewhere. So I think this is probably a big problem with international governance of continental margins. Another example is the opening of the Northwest Passage. It poses new issues with governance of continental margins. So the Northwest Passage, as the Arctic ice sheet or ice sea ice retreat, there will be an opening of these passages for shipping. So Singapore is very interested in this. So opportunities and risks must be carefully balanced in a region that is once remote, sparsely populated, environmentally harsh, ecologically fragile, and climatically sensitive. You know, or the black carbon from the shipping deposit on ice, that will increase ice melting by I don't know what fold, but anyway, it's a very significant amount. And the new governance structures need to overcome the mismatch between applicable boundaries of involved sectors. Okay, so at this stage, it's fairly depressing, I would say. The prevailing law of the sea is incapable of resolving the challenges. The priority issues include investment reform. At present, investors may knowingly engage in legal but profitable activities. Okay, I think private companies provide of some historical evidence for that, but between similar practices are probably undertaken by enterprises involved in marine exploration, especially on common markets. But there's hope. Okay, on my slide here, I read in the Wall Street Journal on the 19th of June, the Deutsche Bank ruled out offering any funding support for the massive port extension in Albert Point, Australia, a coal port adjacent to the Great Barrier Reef. So I think this kind of thing needs to be really promoted, and everybody should know about this kind of thing, this kind of practice and suppress it, extend the problem from the beginning. And risk reduction is very important. Current governance arrangements are ill-suited to deal with the escalating risk and global sustainability implications arising from intensifying current market use, and this necessitates focused, action-oriented research. So I'll give you one example of such research. I think a tool should be developed for focused, action-oriented research. One of them is so-called gap analysis. I think that's being used for U.S. conservation department or something. So essentially, we should bring knowledge from different sectors together in certain areas, especially on the margins. So perhaps one is the development map from the business sector, also from the ecologists, the map of ecosystem services, ecosystem generation and ecosystem sensitivities, and also from this community, the global change hazard map, for instance, the acidification and severity. Then we bring everything together, superimposing the maps, and we may see hotspots of vulnerability and or lack of governance arrangement. Okay, so, and finally, for the law of the sea, I think there's a need for jurisdiction, equity, and the fiscal responsibility. The cost burden and equity applications for coastal states versus those lacking, access to continental margin bounty needs to be better understood, rationalized, and institutionalized. So many of the Pacific Ocean islands lease out their rights to countries far away. I think there has to be a better arrangement for this kind of cost sharing and also risk sharing among them. Okay, so we come up with a 5-point strategy for research strategy towards sustainable margins. To better understand common margin social ecological systems, to develop practical guidance for sustainable development and use of common margin resources, to design governance regimes to stem unsustainable practices, to investigate how to enable equitable sharing of costs and benefits from sustainable use of common margin resources, and to develop alternative research approaches and partnerships that address the challenges faced on common margins. Okay, I stop here. Thank you very much.
We have time for some questions.
Okay. Well, thank you very much for the great presentation. In particular, I'm very excited about the last 5 questions, and that you bring to this morning here a little bit the agenda on sustainable development for ocean and coast. And I think that is a sort of an avenue that IMBER research might want to take advantage of as the global leaders around the planet are convening at the UN to define sustainable development goals. And I think ocean and coast will be one of them. I think that we'll be looking for Lloyd's, IMBER, Clyra, and others to actually provide the science underpinning the solution space. What are we going to do in the face of environmental change? I really want to congratulate you to bring this to the assembled audience, and hope that IMBER and the IMBER science community during this week will discuss this more, what the role of IMBER science should be in the face of these challenges.
Thank you so much for your appreciation. And I'm a chemist by training, so many of the jargons really they don't come from me, but from my colleagues. I think I found it really rewarding to interact with people of different expertise. And so sometimes people are reluctant to step out of the comfort zone to deal with people we don't know very well. But I think I just guarantee you it will be a very rewarding experience to interact with people like that. And also, I mean, bring our science to the human dimension or social sciences. I think they will appreciate. And then eventually, I think we can collaborate to solve some of the problems.
Other questions or comments?
Yes, thank you very much. I'm very happy to hear the discussion on continental margins, because so much is happening here. They're so essential, and they are becoming increasingly populated by, well, just along the coast, and the problems of atmospheric deposition and freshwater runoff, and just pollution, that's penetrating the coastal waters, and that affects species that are depending upon those coastal and estuarine regions, and thus oceanic or open water fisheries. And I think that one of the governance issues is really one that addresses our lifestyle. And the fact that automobiles and affect freshwater runoff and atmospheric deposition is something that I don't know how you go about changing, but hopefully that will also be something that at least is discussion.
Yeah, we cannot change things immediately. At least we should expose the problem. We cannot hide from the reality. Well, we have to expose those risks. I think not just the interaction between social sciences and natural sciences. Actually, a different different disciplines in natural science also need to be more collaborative. For instance, the hydrologists really collaborate with the oceanographers. The hydrologists work on land, and oceanographers work in the sea. They don't talk. But here, I think we see that the headwaters really impact on the coastal ocean. So if we need to solve problems, for instance, those coastal dead zones, we need to know more about the land policies and also the buttons we need to push to really change the regulation. Now, I think in our group, we lack any expertise in legal systems. So we really need someone to know how to engage with the legal system and to make the right calls and in order to make changes.
Thank you, KK. Can I just take up your last point there? I want to talk about governance. You can talk about the policies, the politics, the administration, and the legislation that we have. When we look at these systems worldwide, which we've been doing, what we always find is that most countries, and certainly most developed countries, have got enough of those. We've got enough legislation. We have legislation and governments going from international to regional groups like the European Union to national and local groups. Usually we've got enough of it, and we've got governments that cover both aspects. What we're just not very good at is implementing it. It's the enabling of it afterwards. And I guess there's always a phrase in governments that where there's a will, there's a way out. And I think it's our role as scientists, especially those that are trying to link the natural and social sciences, that are trying to look at the barriers to implementing it, that government. And I think that's the challenges that we've got. We've got enough of it. I mean, people are really now complaining we've got too many laws and regulations. We've got enough of it. It's just that we're not very good at implementing it.
Well, thank you very much. I think that's a very good point. However, I think that in Europe, probably it's most advanced in the world. In other places, I don't think there's probably enough governance arrangement to really for people to realize that they are really out of their boundary. For instance, I think one example here. I think I'm not trying to say anything, but here just one very good example. While for the North Sea, DIN and also DIP loading decreased this year, that's due to the water quality directive of EU, while some other rivers still continue to discharge tons and tons of nitrogen into the coastal ocean. I think this kind of a comparison will really enable people to understand that things can be done. Well, not just if we just shut down the fertilizer factories or do anything drastic. I think European farmers are still doing pretty well, right? So I think some other places the farmers can also use the similar technology and not to pollute the planet so much.
One final comment or question?
Yeah, thanks for the very inspiring talk. I have a question about the natural heritage actually. So there's a lot of talk about sustainable use and exploitation of the oceans, and also economic growth by making use of the oceans. But where is the protection? Where is that? Is there something like sustainable protection of the natural heritage or not? I mean, it more or less vanished from the discussion I can see. And this is the thing. So are there still places, beautiful places in the coastal ocean in the future to visit, or is anybody taking care of those, or can we only read it in books in 50 years?
Yeah, I don't answer, but I think there's one bright side. I think I read it somewhere that Obama has extended the Pacific protect region by 10-fold or so. I think probably that's the way to go, right? If that gets accepted by the Congress, okay, or approved by the Congress. Okay. Well,
Okay, I'd like to thank KK and the Content and Margins Working Group for putting this together. Thank you. We're now breaking for coffee. There's coffee either side of the room and reconvening in the parallel sessions at 11 o'clock.
Well done, Eileen.